Hi guys, this is Rajesh. Today we're going to learn about the DC motor, its working construction and the principle behind it. Let's quickly start with the DC motor. There are many applications that we have with the DC motor like toy cars, trimmers, etc. Before we start discussing about the DC motor, let's see some basics behind it. If current flows through a conductor, as you can see in the diagram, the current is flowing from positive terminal to the negative terminal. It produces a magnetic field in a circular shape. Now, to find the direction of a magnetic field, we use right hand thumb rule. Here, thumb represents the direction of current, whereas the finger represents the direction of magnetic field. If you see in this conductor, the current is flowing downward. If we apply right hand thumb rule, then you understand the direction of magnetic field. Now let's see, what if current flows through a circular coil? If the current flows through a circular coil, then the magnetic field lines produced by the current is linear, which is similar to the magnetic field lines of a permanent magnet, which flows from north to south. Now we'll see why the magnetic field lines provided by a circular coil is linear. So as you can see, we have already discussed the current flowing through a conductor, a straight conductor provides a circular magnetic field. So what if we make the straight conductor into circular coil? At individual point, there is a circular magnetic field, as you can see in this diagram over here. At this particular point, it gives you a circular magnetic field. Even at this particular point, you have a circular magnetic field. But this magnetic field gets added with this second magnetic field and provides a linear magnetic field. See this diagram properly to understand the concept. So you can see very clearly that the magnetic field provided by the conductor at this point is circular, and the magnetic field provided by the conductor at this point is circular, and they both get added together to provide the magnetic field, which is similar to the magnetic field provided by a permanent magnet. As we have already discussed that a current carrying conductor produces the magnetic field. If this magnetic field produced by the conductor gets closer to a permanent magnet, they both experiences a force. Now, the principle of motor says that a current carrying conductor in the presence of a magnetic field experiences a force. Now let's jump into the concept of DC motor. Here you can see the simple diagram of a DC motor where you can see different components like a stator, which is a permanent south and a permanent north pole, armature, which is nothing but n number of coils, and the brushes, which is resting on the commutators. So the commutator ring, you can see, is split into two parts with an insulation between, and that's why we call this commutator ring as split ring. Yeah, and this motor is connected with a power source, which is a DC power source, positive end and the negative end. And we know that the current always flows from positive terminal to the negative terminal, and you can see the current flows through the brushes, through this commutator C1, through this conductor, and coming through this brushes B2, through this commutator C2, and to the negative end of the battery. And you can see here that a current carrying conductor in the presence of external magnetic field experiences a force, as we have discussed before. Now, to find the direction of this force, we have a rule called Fleming's left hand rule. So Fleming's left hand rule says that the force can be determined by understanding the direction of the current and the direction of the magnetic field. So you can see the middle finger represents the direction of current, and the index finger represents the direction of magnetic field, and the thumb represents the direction of force. So with the help of Fleming's left hand rule, we can identify the force acting on the conductor. Let's apply this Fleming's left hand rule on this motor. So I see the armature can be considered as the conductor AB, BC and CD. If you apply Fleming's left hand rule on the conductor AB, you'll find the force is acting upward, whereas on the conductor CD, the force is acting downward. So these two opposite force gives you torque action. Now what about the conductor BC? What is the torque acting on the conductor BC? You can see that the current in the conductor BC and the magnetic field is making an angle of 180 degrees, which means they are parallel to each other. If the current and the magnetic field are parallel to each other, from the torque equation BIL sine theta, theta represents the angle between B, which is magnetic field, and I, which is current. The theta represents the angle between I and B. If theta is equal to 0, the entire torque becomes 0. And if theta is equal to 180 degree, that also results the torque equals to 0. So therefore, the torque acting on the conductor BC is equals to 0. Therefore, the force on the conductor AB, which is upward direction, and on the conductor CD, the force in downward direction, results the motor to rotate in a clockwise direction. Now as you can see, after 1/2 rotation of the motor, the commutator C1 over here goes to the right side with the rotation of the coil, and the commutator C2 goes to the left side. So you can see over here, the commutator C1 is on the now right side and the commutator C2 goes to the left side. Whereas the brushes, they are the static part, they are still connected with the positive end, the brush B2 is connected with the negative end. So now the current flows from positive, goes to the commutator C2, flows through the conductor DC, and through BA goes to the brush B2 and comes to the negative terminal. Now you can see that the current direction previously on the left side of the conductor was like this. Now even on the left hand side, the current direction has not changed. So if the current direction didn't change and even the magnetic field direction didn't change, so therefore the force direction remains same, which means on the left hand side of the conductor, previously the force was upward, even now the force is upward. The force was downward on the right side. After half rotation, the force is downward on the right side. So the torque action remains same, which means previously the torque was clockwise, remains clockwise even after half rotation. And you can see here how the opposite torque creates the rotational force. Yes, but this is the point where you can see this torque and the downward torque are exactly in opposite direction, like this. Hence give the torque equals to 0. To avoid this, what we do is we add one more coil, which makes the torque available all the time in the motor, as you can see in this diagram. You can see that if these two forces cancel each other and gives the torque equals 0, the other two forces are acting downward and upward, which gives you the torque action. So therefore, even though you have a torque equals 0 because of the perpendicular coil, the horizontal coil gives you the torque action. Hence, the torque is available all the time. Thank you so much.